Hello everyone, I am Professor Patrice Chartrand, co-developer of FactSage, and with Chris Bale, I'm happy to present to you what's new in FactSage 8.1. The presentation will be divided in three parts. In the first part, we will discuss a major change we did in the modules of FactSage, then changes about the physical properties, and the last part of the presentation will be related to changes in databases. So concerning the different modules of FactSage, well, the major change in FactSage 8.1 is the introduction of virtual elements in the equilibrium, phase diagram, compound, and solution modules of FactSage. So the virtual elements are basically elements with symbols starting with a capital Q and followed by a lowercase letter from A to Z. So you can have up to 26 of these elements, and they have an atomic weight of 0. They can be added directly at the interface or in databases to a chemical formula in order to constrain the elemental balance to force certain compounds to be non-reactive or reactively constrained. For example, in an aqueous solution, you may want, for example, to affect the redox of sulfur species in the aqueous solution. This can be done with virtual elements. If you're heating a crucible that can, for example, not dissolve or not react with its content, but have the thermal effect absorbing heat from reactions, it can be done with virtual elements. Preventing unwanted reactions, preventing some internal equilibria in a solution, like a spinel, following the course of a reaction with time by defining the number of moles of species containing the virtual elements. You can then decide how some reactions are progressing as a function of alpha, which can be related with a time variable, for example, in the equilibrium module. Para-equilibrium calculations, but also to some degree some surface tension calculations can be done with the addition of virtual elements. So one example, you have a fine zinc powder that is mixed intimately with a copper oxide powder in a corundum crucible. You're igniting the reaction, and the reactants are initially at 20 degrees Celsius, and you would like to know what is the adiabatic temperature of the system, including the corundum crucible, if you assume that corundum crucible is not reacting chemically, or does not dissolve, but it equilibrates thermally with the products. In order to do that, you create a new user database like the QBase here, and you copy from FT oxide or FactPS the alumina compound, which will contain the S4 corundum phase. Inside the database, Q database, you go to tools and you copy alumina compound and you add the QA element. It could have been QB, QC. You don't need the parentheses, but the parentheses here are to highlight the presence of the virtual elements. All the faces of that compound are copied with their properties. Now you can delete the normal alumina from the database, which only contains now the alumina compound with 5 faces and is associated to 1 mole of QA element per mole of alumina. And the QA element has a 0 mass, so it does not affect the molecular mass of your alumina compound. So you go to equilibrium. Now you connect the Q base to the calculation with FactPS and FS copper, for example. And now I'm entering 200 grams of my crucible, which is alumina QA compound, and I select the phase corundum at 20 degrees Celsius as a reactant with initial conditions. And I'm adding 50 grams of both the zinc powder and the copper oxide powder at 20 degrees Celsius. Now in the selection of compounds, I will see appearing the new alumina QA species in different databases. The way it's done is we automatically take the alumina faces and add the QA species in the FSCOP database, but there is also the QBase database that I just created. So I select in this case corundum S4 from my QBase database. When I perform the adiabatic calculation, delta H equals 0, looking for temperature, it finds 320 degrees Celsius. And you can see that the FCC alloy is formed with zinc oxide because of the exchange of oxygen between the powder. It's exothermic, temperature rises, but the alumina crucible stays at 200 grams. Obviously, the temperature would have been much higher if there were not 200 grams of alumina to absorb the heat of the reaction. Please note the alumina did not form the ZNO-Al2 three-phase here because it's not allowed to react, as there is no other places to put the QA species, QA element. Virtual elements can also be used to compute or constrain some reaction, for example, to compute the liquidus temperature of an equimolar mixture of sodium nitrate, sodium nitrite, sodium perchlorate, and sodium chloride in air. So there is an internal reaction in the liquid solution and in other phases involving the nitrate and perchlorate, which is a reduced and an oxidized species, to form the neutral species, oxidized NaNO3 and NaCl. The delta G of this reaction at high temperature is very negative, so it should proceed thermodynamically. In order to constrain it kinetically, we can use virtual species. How to do that? I have an equimolar mixture and I would like to know what's the liquidus temperature. So if I permit a full equilibrium reaction, obviously this reaction will proceed. And I will compute, in this case, when I get 100 moles of air with 4 moles of the salts, a temperature of liquidus of 561 degrees Celsius. It's on the sodium chloride liquidus. And initially in the reactants there was a partial pressure of oxygen of 0.21 atmosphere. However, in our case, it's a slightly higher pressure because of the decomposition of the perchlorate. Now, if I want to constrain kinetically using virtual species, I simply have to add a virtual element to my 4 salts. Randomly, I put QA, QB, QC, and QD to the 4 different salts. Now, none of them can react because they are associated with an element that can go nowhere else than in that phase. So if I compute now the equilibrium, I will find that the liquidus temperature is at around 460 degrees Celsius and the partial pressure of oxygen stays at 0.21 atmospheres. The reaction is then constrained. So please have a look at our 15 new documentation slides that have been added for virtual elements. And there are several examples in the list here you can find in the documentation, a slideshow of FactSage. Now for physical properties, a small but important change at the interface level is before 8.1, the computation of physical properties was automatically linked to the computation of the molar volume properties and vice versa. So if you wanted to compute volumetric properties, you had to have physical properties added too. Now in 8.1, you can see that 3 options are possible: compute without volumetric properties, compute only volumetric properties, or compute with volumetric properties and physical properties. Physical properties cannot be computed without volumetric properties, obviously. So in the Equilibre module menu window, please select the options that you want active for the calculation. So the big addition in 8.1 in terms of physical property is the modeling of thermal conductivity of phases and phase assemblages. This is very different. The thermal conductivity of a phase will depend on its structure and some of its properties, but phase assemblages is more complex as porosity, grain size, and other variables may be included. So for the moment, the current limitations are we can only compute pure solid or liquid phases that are insulators. These are non-metallic phases because we don't yet have an electronic thermal conduction model implemented in FactSage. We're working on it. So the thermal conductivity of these phases are automatically calculated in the Equilibre module when the physical properties are asked to be calculated. as I showed previously. However, if there are more than one phase at equilibrium, then a phase assemblage must be considered. So the thermal conductivity of the phase assemblage is computed in the equilibrium module as it provides the amount and the volume fractions of the different phases. But we need more than that. We need simplified microstructure for assembling these phases together. And we propose 5 different outputs. 2 of them are limiting cases, like the parallel microstructure of the series microstructures, but 3 of them are related to more or less random states with spheres or ovoid shape factors if necessary. So the way we compute the thermal conductivity of phases is first we have a model for temperature for every phases that are stable. Then using a user input grain size, diameter average grain size, we can compute the impact of the grain size on the thermal conductivity, which starts to be big below 5 microns typically. And we have the intragranular porosity, so within a grain of a phase, which is single phase, if there is an intragranular porosity, its effect will be taken into account. So with these 3 steps, we can calculate the thermal conductivity of a pure solid substance with grain size, temperature, and internal porosity or intragranular porosity. The next 2 steps are done automatically to compute the thermal conductivity of phase assemblages. This is done by considering the intergranular porosity, which will be user entered. And this has a very strong effect, and there are some critical phenomena here. Beyond a given value of the intergranular porosity, there is a steep decrease of the thermal conductivity. But also we have to take into account the phase volume fractions, which are computed by equilibrium. And the models there provide 5 different thermal conductivities, 2 maximum and minimum limit. The upper maximum limit is given by the parallel mode, which is the most absolute value you can get. The minimum lower limit is a series microstructure, but in between we are using the EMT approach, which is our recommended value for the thermal conductivity, which lies between the 2 upper and lower minimum and maximum limits. And we are using the Ashin-Strickman approach to have an upper recommended value and a lower recommended value, which are lying between the recommended values and the 2 limits. So with this 2 extra steps, we permit to calculate 5 estimations of the thermal conductivity of a phase assemblage of pure solid substances or liquid substances. So this is a big addition in FactSage, and as you will see in the database part, we added many thermal conductivity parameters and volumetric parameters, which are necessary to compute the thermal conductivity in our databases. So in order for the user to provide information about the microstructure, we created a microstructure module, which will permit you to enter the grain size, intergranular porosity, intragranular porosity, and critical porosity values. You simply go to your FactSage directory, the main directory, and you will see a microstructure.exe module. Please double click on it and you will see here appearing this small simple interface where you can enter the values you provide yourself, and they will apply to all different phases that are calculated. Don't forget to save to file, and this is storing the data for the upcoming calculation in a temporary file. All the other phase-related information, like the Debye temperature, the Gruneisen, which are necessary in our model to compute the thermal conductivity, they are stored in the compound databases through the compound module. So in equilibrium, how is this calculated? It's calculated first by the user entering in the microstructure module the grain size and the different porosities that are necessary for the computation. Then you go in equilibrium and you set up your reactant, you select the pure solids and liquids, you fix the temperature, pressure, alpha, beta targets. Don't use solid solution at this step. Unfortunately, we don't have yet a model for that, but we're working on it. And once you click on Calculate of equilibrium, it's going to the compound module and is retrieving all the important information for the computation of phase equilibrium and the thermal conductivity. And it's outputting the mass, the volume of the phases and their temperature and pressure. Then the FISPROP DLL is called by Equilib with the information about masses, volumes, and temperature of the phases. And FISPROP is using the microstructure data to compute the thermal conductivity of the phases. Now, using the thermal conductivity of the phases, it computes the thermal conductivity of the phase assemblage, and it stored the results, the 5 different values for every calculations are stored in FISPROP thermoresults.ini file, which you can open. It's an ASCII file, and you will see all the results at all the temperatures, values of alpha and beta that are stored there. As an example, here is a reactor with 2 refractory linings. One is a chemical layer or working layer, and the external layer in yellow is the insulating layer, thermal insulation. Now, these 2 layers have the same phases with the same composition: 60% quartz, 35% corundum, 2% rutile, and 3% hematite. So you go in Equilib, you set up an amount, a basis of calculation, set a temperature of 300 degrees Celsius, and in the microstructure module, I fixed the grain size to be 100 micron. I fixed the intragranular porosity to be 0.1, which is 10%. And for the working layer, I do a first calculation with a 10% intergranular porosity. So this is a denser material for liquids not to penetrate the layer. If I compute the recommended thermal conductivity with the EMT model, I get 8.5 watt per meter Kelvin. Now, if I change the intergranular porosity to 40% for the insulating layer, so then I get a much less dense material with the same grains. Basically, I compute, Equilib will compute for me a thermal conductivity which is roughly 10 times lower. So it's important to note that the quartz, corundum, rutile, and hematite grains here, they have the same thermal conductivities in both examples. It's really the phase assemblage that is different. And this is consequent with the real system. In terms of databases in 8.1, here are the updates. In the FactPS Pure Substance Compound database, we added a few new salts, but the main change is the volumetric properties, so thermal expansion, compressibility, derivative of bulk modulus, density at room temperature, and the thermal conductivity model parameters that are added for 54 liquid salts, 44 solid carbides, 42 solid nitrides, 36 solid borides, and as you can see, these are binary carbides, nitrides, and borides, but also 149 solid salt compounds, including some ternary salt compounds, like some perovskites and so on. So with this, you can use the thermal conductivity model, the microstructure module, to compute the thermal conductivity of phases and phase assemblages. In the FT-Lite database for aluminum and magnesium alloys, we added most of the cobalt rare earth binary systems. They have been integrated there. This is important for calculation involving production of magnets, recycling of magnets. We have updated several important phases and solid solutions there, a lot of new systems. And we added the volumetric and thermal conductivity model parameters, not for the alloy intermetallic phases, but rather for ceramics that are present in these alloys. So we have 23 carbides, 24 nitrides, and 55 solid borides that have been added there. Also in the FT-Lite database, for the liquid solution, FT-Lite liquid, we have a viscosity model for aluminum, magnesium, copper, silicon, zinc, evaluated up to the quaternary systems. It has been modeled, but you can reasonably add the viscosity of some minor alloying elements or impurities, silver, chromium, iron, gallium, indium, potassium, lithium, manganese, sodium, nickel, lead, tin, and zinc. No, this is not zinc, sorry, it's zirconium there. In order to calculate the viscosity, don't forget to use volume and physical property data in the Equilibre menu page. FT oxide are important database about oxides. There's a big addition of vanadium oxides to the slag, VO, V2O3, VO2, V2O5, and some solid solution in the vanadium, sodium oxide, calcium oxide, magnesia, alumina, iron oxides, and silica. So if you want to compute the distribution of vanadium between a slag and a steel, a liquid alloy, it can be done with FS steel. We also made modifications, updates to alkali oxides, titania silica system, mostly related to titanium oxide containing binary alkali or sodium oxide with silica. So we have 50 new stoichiometric compounds, 3 new solid solutions, vanadium containing spinel, VO-V2O3 and VO2-VFO4 solid solutions, and have been added, and we also modified the monoxide and corundum phases and around 10 compounds. FT salt database, the major modification is to the salt K list involving nitrates. We added nitrites to nitrates. This is for mainly for solar application, but also fertilizers. So if sodium potassium nitrates are used as a thermal medium in solar systems. It includes the addition of chlorides, carbonates, but also perchlorates. We have a perchlorate solid solution of the 2 sodium potassium base salts. It's mainly focused on nitrate rich solid solution, but you can do decomposition to air to have the nitrite equilibrium value and also the additions of impurities in it. Also in the FT salt database, volumetric and thermal conductivity model parameters were added for 52 molten salts and 142 solid salts, again including several ternary salts. A lot of them were calibrated from first principle calculations, giving good results there. The FS Steel database, major updates have been done to the FCC, BCC, Sigma, and Lavis C14 solutions, mainly in the cobalt, chromium, iron, manganese, nickel, vanadium, tungsten system, aimed at applications for high alloyed steels, but also high entropy alloys. So we are talking about here 22 new binaries and 41 ternary systems, 25 new solution phases, 38 new compounds added. You have the list here. As you can see, it's quite diverse in terms of new binary systems, updated binary systems, and updated and new ternary systems. Some important classical systems, I would say, are present, as you can see, involving major elements like chromium, iron, and nickel, and carbon in the steels. The SPMCBN database from the Spencer group for refractory carbides, borides, and nitrides and silicides has been modified for the following binary subsystems, either new systems or revised binary optimizations. And revised or new ternary optimizations are present for aluminum-based, cobalt-based, chromium-based, iron-based, and hafnium-based systems. You get the complete list here. This is the work of the Spencer group at the Spencer in Trumansburg near Ithaca. Also, the database benefited from our new thermal conductivity and volumetric model properties. By the way, in all databases, we get the same parameters that have been put. So in this case, we have 30 solid carbides, 29 solid nitrides, and 125 solid borides, which were added to the database. Please note here we get the ternary borides, ternary nitrides, ternary carbides that are also added in the database, which are not necessarily in the FactPS database. So in summary, what's new in FactSage 8.1? Virtual elements for constrained equilibrium calculation. There's a lot to read in the documentation about this. It's an exciting new feature. A new thermal conductivity model has been developed for pure and solid and liquid insulator phases. This is important for computing the thermal conductivity of a given phase, but also phase assemblages. You will have to master the microstructure module to compute the latest. We have a lot of model parameters that have been added in most of our databases for volumetric and thermal conductivities. This is in the FactPS, FT Oxide, FT Light, FS Steel, and SPM-CBN databases. Also in the databases, we have thermodynamic models that have been thermodynamic model parameters that have been changed or added. In FT Light, cobalt rare earths binary subsystem, viscosity of aluminum magnesium alloys, the major alloys, but also minor solutes. In FT oxides, big changes for vanadium oxide containing slags, but also with alkali titania containing slags. In FT salt, an exciting new list for the thermal medium of nitrates or fertilizers, including decompositions to nitrites and chlorides to perchlorates to chlorides. And FS steel, updated FCC, BCC sigma, Lavis C14 for high alloyed steel, but also high entropy alloy. And in the Spencer Group SPM-CBN database for refractory materials, 78 new or updated binary and ternary systems. So I hope you will enjoy these new updates, and looking forward for FactSage 8.2 with many new updates coming. So I salute you, and Jean-Philippe Harvey will answer the questions about what's new in FactSage 8.1.